Thank you. And also, so in the time between when I sent them my resume and now, I actually am co-leading the hardware for the DOE Exascale program, so I'm stepping down as CTO for NERSC. But hey. All right, so I'm going to go through the initial part pretty quickly, but I still wanted to put in context. I see students, and so I always like to leave in the necessary slides that a lot of us have already seen too many times. But you know, the first is, of course, that if you just follow the top 500 list over the past 2.5 decades, we've come used to improvements in performance that approach about 1,000 times improvement in terms of, well, according to LINPACK, which people can debate about, but 1,000x improvement in performance every 11 years, like clockwork, for about 20, 30 years now. And we've come to rely on this for not just improvements in resolution for our scientific codes, but in fact transformational changes in our ability to do modeling. We haven't just improved resolution, we've added complexity, new species, and the kinds of physics breakthroughs that we expect to have in the future require continued scaling of performance improvements. But you know, kind of this was the shot across the bow, and this has been shown so many times. I think the first time I showed it was at an ISC in 2006, and we had an earlier version of the graph that was hand drawn by Herb Sutter, but the issue is that we still have Moore's law scaling for now. I know that Satoshi told you you're not going to have it for much longer, but in the meantime, we still see scaling in the number of transistors. And can I borrow a pointer from somebody? I forgot to grab a pointer. It's all right, let me try to use the mouse here. Can you see that? I also have to move very carefully because of this ear mic thing. All right. So, you know, we still have this exponential improvements in, I'm just going to, yeah, okay, there you go. Thank you. Yeah, so we're seeing these exponential improvements. You know what, oblique angle, I'm just going to go back to this guy here. All right, exponential improvements in the number of transistors we can cram onto the chip. But we hit the Dennard scaling essentially ended in 2004. And Dennard scaling was our ability to improve the energy efficiency of individual transistors at a rate faster than we were cramming them onto the chip. And so we took up the slack by cranking up the clock frequency at an exponential rate every generation. And of course, we can no longer do that anymore because of the end of Dennard. But the industry found a different way to continue technology scaling. So instead of scaling up the clock frequency, we doubled the number of cores every generation. I was involved in a study with David Patterson's folks that we started in 2003. And in 2003, we were going to skewer industry. We were going to say this idea of going with scaling, doubling the number of cores every generation is just stupid. Everybody's run out of ideas. And by the end of a 4-year study, we determined actually it wasn't such a bad idea after all. And moreover, maybe you should go to lighter weight cores, which we'll get into. And of course, Satoshi has already covered this, but you know, coming around 2025, might not even have the Moore's law anymore, and this will make things even more intriguing. The net result, though, is that we have an expectation gap. We've come to expect these exponential improvements in performance, and yet we're probably not going to, if we continue on our current path, we're not going to be able to get the kind of performance improvements we need to advance science. So the challenge here, and now we're done with all of the context stuff, and everybody's also managed to filter in, so worked out perfectly. The challenge is that, you know, the nature of digital computing systems is changing rapidly due to the end of Dennard scaling and towards the close of silicon lithography as we know it. And our existing programming environments were designed with a machine in mind that is 30 plus years old. And all of the things that we had in mind, the design constraints for which our languages, our software environment, our applications have in mind a machine abstraction that's nearly 30 years old. And it does not reflect what is emerging as we move towards the exascale. And it's also important that as we migrate our software environment and our applications and algorithms to exascale, that we extrapolate to 2025 and beyond in order to come up with durable design. Because you could find yourself porting everything to, whatever the architecture is that's currently on the floor, and then constantly having to change over and over again. You'd really like to think in terms of extrapolating what the longer term trends are that go out 15 years, so that when you do your redesign, you come up with a durable set of abstractions, something that you can actually continue with over the next 15 years instead of making it work for each. So, we've talked about the DOE strategy. We've decided to adopt a holistic strategy for these challenges, which involves co-designing the hardware, the applications, and the programming environments together. And the reason why is that we don't actually think that we can ask the hardware architects to accommodate all of these changes and preserve our current software environment. You could do it, but you will not see particular gains in performance that we need. You also cannot expect the software, the application programmers to eat it all and program in exotic or strange and rapidly changing programming environments. It really requires a constant trade-off evaluation together in order to come up with a compromise that minimizes disruption of the applications and maximizes the effectiveness of the hardware. And so, before I get into the hardware changes, and that's going to be the next phase of the talk here, is to really go through the hardware changes and talk with them in terms of not what is the next chip that's coming out, but extrapolating them out to where we will be in 2025. Because our crystal ball has gotten a lot clearer since over the past decade. The first thing is that to not conflate physics challenges, which is like the end of Dennard scaling, with computer architecture challenges. A lot of my colleagues over the years have said, oh, you can't get the computer architecture guys to change anything. They got their gamers in the consumer market. And then he said, well, what would you want to change? Like, well, I want, more capacity and I want it at a terabyte per second. You're like, well, that's kind of limited by physics, and these guys are trying, you have to understand that the computer architects are trying the best that they can with the physics limitations that they have. So, physics is technological constraints. There is a cost to data movement. I can't magically make the resistance of copper wire improve. That is a physical constraint. The capacity of DRAM cells, clock frequencies at the end of Dennard scaling, speed of light, the melting point of silicon are physics constraints, and the computer architects have to work within that box. Computer architecture is the design of the machine, and so you can put in power management, you can make changes to the instruction set architecture, you can make design choices about SIMD widths. These are the things that, in fact, if you talk to the architects, they can, if you talked with NVIDIA, they'll make the change within 18 months. We convinced them to double the number of registers per thread, and they got it in within 18 months of us having that debate with them. Computer architecture is a data-driven process. If you can come to the table with quantitative evidence that justifies a hardware architecture choice, then you actually have you can actually move things. And Fred Brooks said, computer architecture is like all other architecture, like architecture of buildings. It's the art of determining the needs of the user of a structure and then designing to meet those needs as effectively as possible, but within economic and technological constraints. And there's a lot that you can change. There's a lot that you can still do now to affect the future of architecture, but within the constraints of physics. And so that's why we really believe in co-design. If you believe that both the hardware architecture choices can be influenced and worked together with making changes to the software, then we can really make create a more productive environment in the long term. So, you know, changing hardware is very expensive and it takes a long lead time, but also rewriting your software is extremely expensive and also takes a long lead time. Co-design is basically making quantitative trade-off analysis using trustworthy models or simulation in order to evaluate the cost and the cost of these changes in an environment that is constrained by physics and by cost. And so in this, you know, architecture modeling and simulation are really important for creating credible information to evaluate those cost trade-offs. So that's my shtick about, you know, co-design and background. So let's move into the meat here. So we're going to talk about architecture trends over the next 15 to 20 years, and what I think the Exascale node is going to look like, and then we're going to turn it over to the implications for our programming environment and how we can do much better. So I get together with Peter Kogi ever since the 2008 DARPA report. We get together and reevaluate, did all those really depressing diagrams that he put together continue, and so we collect new data and discover that yes, it continues. And so, you know, we can't crank up the power dissipation for these chips. It's not very practical. So clock frequency growth has tailed off and the number of cores is going up. This is a really old diagram that I created in 2005 when I was with the Patterson study. It was at the view from Berkeley, as we called it, to explain really why this isn't such a completely stupid idea to increase, you know, double the number of cores, and for that matter to go to lightweight cores. And the way it works is this, is that, you know, V squared F. So, you know, with Dennard scaling, you could drop the voltage and you'd get this cubic effect where I could reduce the energy required by the voltage squared. But if I can no longer drop the voltage, then I only have the frequency term to work with. So it used to be I had a cubic, you know, so I lower the clock rate and I can actually operate at a slightly lower voltage, so I can get a little bit of that cubic improvement back. And so we start from like a power 5 here, really big chip. If you just look at this chip here, that guy up here in the corner, that's a floating point unit. All the rest of the surface area in that chip is to hide the latency and to handle the high clock frequencies. It's the pipelining, it's caches, all sorts of stuff to feed that little teeny floating point unit. If you slow down your clock rates modestly, like you do with, let's say, an Intel Core 2, which was contemporary at the time that I made this slide, then you not only recover some energy efficiency because of the capacity of the transistors, you also get to reduce the depth of the pipelines. And now I reduced the surface area of the chip, so I've reduced cost. I've also reduced leakage current, which is another source of power loss. And so that's pretty good, but I have a quad issue processor core, but my CPI, my is still very low. I very rarely actually use 4 instructions per cycle. So if I go to an Atom core, and at the time an Atom core, which is now like the KNL, used to be a dual issue core, or even a single issue core. Same ISA as an Intel Core 2, but I've simplified, I've reduced the complexity of the chip, and modest decrease in net performance, but huge reduction in area. And then if I go to a specialized processor, I use Tensilica as a stand-in for GPU core, then I can have further improvements. In fact, the way it plays out is I go from 120 watts at, this is 90 nanometers, so 120 watts at nearly 2 gigahertz. I take all these modest reductions, I get down to like a GPU core, 0.09 watts at 600 megahertz. That is a peak improvement of 400x improvement in peak efficiency. If I ignore the memory subsystem and things like that, when I did sustained efficiency, I get an 80 to 120x sustained efficiency improvement, but I'm still hampered by my DRAM technology. But regardless, when it comes to the chip, this is the right choice because each simple core is a quarter as computationally efficient as the complex core, but you can fit hundreds of them into the same chip and the same price point, and be 100 times more, a peak of 100 times more energy efficient. Net, it ends up being like 10x, but with all of the burden of other subsystems. But there's a peak that you could extract out of that might be closer to 100x. And the result is that this is, the classic graph from the DARPA report. We're trying to cross that 20 picojoule per flop finish line here, and the only way that you're going to get to that is either lightweight cores or accelerator cores like GPUs. And that's of all of the scenarios studied, that's the only thing that crosses the finish line. You can continue with the conventional x86 or large core architecture. They will still make them in 2025, but you will consign yourself to this gently tailing off improvements in performance. This graph, by the way, looks almost identical to a graph I saw when I started my career 25 years ago, when we were showing parallel cluster type computing versus vector computing, that you could continue with vector computing, but you would consign yourself to that shallower curve of performance improvement. So NVIDIA has this term locks and tocks, and I actually kind of like it because it doesn't say one core is better than the other. It says, okay, I have a latency optimized core, so I still have my fat cores, my Xeons and stuff, and this is the most energy efficient solution if you don't have a lot of parallelism. These lightweight cores, or even GPU cores that I'm talking about, that is by far the most energy efficient solution if you have sufficient parallelism to exploit it. If you do not have sufficient parallelism, then in fact the latency optimized core is the most energy efficient path forward. And so this gets past, core shaming, oh, it's a fat, I hate fat core, thin core, it's like, oh, this core is, needs to go on a diet or something. This is not, it really is, the large complex cores like Power 8 are actually the most energy efficient if you don't have parallelism. But that's not everything that's wrong as we move forward. So, okay, we have, by going to scaling the number of cores and furthermore going beyond just multi-core, we've going to many-core, which is to go with even lighter weight cores than we used to, rather than merely replicating cores of the same size. Now we push the problem to a new area, and the problem is this. The problem is with wires. Copper, which is what we're currently using for our materials, is about as low resistance material as you can expect at room temperature, basically, for these machines. So if you think of this little hunk of metal here, this is a copper wire, and the power dissipated by copper wire is equal to the frequency multiplied by the length of that hunk of metal and divided by the cross-section area. Well, this is just your plain old resistive capacitive wire circuit that you're taught in undergraduate physics. So what's the deal? Well, the issue is that when I use a lithography process, and this is where I get my technology scaling, with lithography, this wire shrinks in every dimension equally. If that happens, you look at this equation, my energy efficiency for that wire is not improving when I shrink it. That's a problem because when I take this transistor, as described by our speaker yesterday, it looks like a capacitor. Well, it is a capacitor. It's a capacitor with an active material underneath, but it's a capacitor. And when you shrink that guy down, the area of the capacitor goes down, and therefore the energy efficiency of the transistor improves. I don't have Dennard scaling. I can't drop the voltage, but I still get an energy efficiency improvement with technology scaling when I scale that guy down. And so if I have my compute, which is the transistors, is improving every generation, and my wires are not improving, it gets to the point that the compute part is not dominant anymore. Data movement now becomes the dominant cost. And this inverts everything that we're used to when we calculate things, we think of flops as being the most expensive component of a computer, and we try to minimize the number of flops that we consume, when in fact it is now going to be data movement, and we've only just begun to develop order of complexity theory and communication avoiding, algorithms theory that takes into account reducing data movement rather than reducing the number of flops. Photonics could break through this bandwidth distance limit, but thus far it's photonics converts a energy efficiency problem into a cost problem, and so we haven't been able to quite deal with that yet, but it is a dark horse candidate. The other aspect is pin limits. So, we have the issue of data movement at a distance. The other is that Moore's law does not work for pin packages. Moore's law has been nominally 30% per year compounded annual rate of growth of the number of transistors you can cram onto a chip. Pins at best are 1.5%, closer to 1% growth rate on a year-per-year basis. So it's hard to get no Moore's law for pins. So if you imagine 4,000 pins in a chip, which is a pretty aggressive pin package, but the GPU guys do this kind of thing. Half of those pins are going to be power and ground, because the thing sucks a lot of watts. Of the remaining 2,000 pins, you run those guys as differential pairs to reject noise. So if you get beyond about, and you're also limited, if you go beyond about 15 gigabits per second per pin, then you go from a resistive capacitive circuit to a inductive, and the losses go way up. You have to have complicated SerDes, all sorts of badness happens. So you try to keep it below 15 gigabits per second. So if we just multiply this out, that's 10 gigabits per second times 1,000 pins. That's about a peak of 1.2 terabytes per second. If we get aggressive and do single-ended signaling and some other tricks, we might be able to crank that up to 4 terabytes per second. But that's there now. If we're reaching an upper limit, and we're already within striking distance of this upper limit of the rate at which you can move data on and off chip with electrical connections. 2.5D integration boosts pin density, but it's a one-shot deal. The way it works here is that, I got a silicon carrier, and I can actually use lithographic processes at like 130 nanometer to increase my wiring density and my pin pad density by a factor of 4 to 8. But that's about it. And so then I take my CPU and I put my memory stacks, and I kind of bond them ionically to the surface of this thing. I increased my pin pad density, so now the CPU can speak to these memory cubes at very high rates. So the individual pins are still operating at 10 gigabits per second peak, but I have a lot more pins now. And if you look at HBM, it's actually just 4 DDR4 channels, conventional DDR4 channels, but I crammed them into a single package. So that's great, but a one-time boost, and also there's limited surface area in these silicon carriers, so I don't get my memory capacity improvements. I do get memory bandwidth improvements, but not capacity, and it's expensive. So maybe there's an in for photonics here. But this is a diagram I created years ago to try to communicate this, but this is cost of data movement relative to ops, and the real point here is that we're improving the energy efficiency of each flop, but moving a small distance in the chip is not improving, and also getting off the chip is only improving at a modest rate, and this really impacts our programming environment. I still, despite showing that diagram, had people saying, well, are you sure it's a problem? How big of a problem is it? Did you really calculate it out? And sadly, I started saying, well, the answer depends. And then everybody started to doubt whether or not this is a real problem. So let's just do this. Let's calculate it out. I'm a double E, and I know how to use Excel. This is a die photo. We've got Intel, big cores. Small core, so ARM said, and Intel, so I talked to Al Gara at Intel, and he said, oh yeah, the RISC-V core that you guys are working on, it's got just about the same power dissipation characteristics as the KNL core. And it's like, great. So can I use a KNL core? It's like, no, you can't use a KNL core. So we're going to use a RISC-V core, which just happens to have the same power and area characteristics as the KNL core. just by coincidence. And the same goes for the Tensilica core. I use this as a stand-in for the GPU. I had exactly the same conversation with Bill Daly in 2009, where he gave me preliminary permission to use a GPU core, and then Jensen saw it, and I removed it, and so the Tensilica core just happens to have the same characteristics. It's just not a GPU core. So, you know, and we have to do some area adjustments, so by the magic of PowerPoint, I actually proportionally scaled these down to what their actual relative sizes are on die, which you wouldn't make as interesting a die photo when you see that. So 0.2 millimeters by 0.2 millimeters, tiny, tiny little things. So if we look at the energy area cost for these guys, it's the same as that 2005 photo thing I had, where we go from 12 millimeters squared at 651 picojoules per operation cycle. So this is the fully burdened, not with memory, but with cache and all the other stuff, how many ops I can graduate per cycle. So this isn't even benchmarked. It's really the peak. We go down to 0.6 or 0.046 millimeters squared at 22 picojoules per op graduated per cycle. So, so huge energy efficiency improvements when you go from these fat cores to thin core. But the key thing here is that the wire energy for all of these guys is the same, 100 femtojoules per bit per millimeter traveled. So how does this play out then? So when I get the fat core, you want to have two metrics that are interesting. I have at what point does a compute operation equal the cost of moving of the data movement? So for Intel Haswell core, we're talking about you'd have to move data 108 millimeters across the silicon, the surface of a piece of silicon, in order for the data movement costs to equal the 651 picojoule operation cost. So when I move data 20 millimeters across a surface of silicon, it consumes only 0.2 times the amount of energy that a flop does. And that's why people are like, what are you talking about? You know, Xeon, I never see these effects that you're talking about. This is crazy. But now if we go to a lighter weight core, I only need to move data 12 millimeters across the surface of the chip before the cost of compute op is equal to the cost of data movement energy. And you'll notice that the Xeon Phi, the KNL, offers a quadrant mode where you can actually divide the surface of the chip up into 4 NUMA nodes. And it's because that's actually 12 millimeters is half the distance across the surface of a KNL chip. Now we go to an even lighter weight core. I only need to move 3.6 millimeters before the energy cost of moving the data is equal to the energy cost of performing an operation. And these metrics will get worse with each generation up until we get to the limits of silicon lithography. And that is why we're worried. So, you know, we have our locks and tocks, and another important thing to understand is that as we move to chips that have hundreds of cores on board the chip, each hop that you take across the surface of that chip also has latency. I have to take at least a couple of cycles per hop. If there's buffering, it might take 10 cycles per hop. So there's a latency cost and there's an extra energy cost. I need to pay attention to topology. And this gets to this. You know, everybody said, well, data locality, that's always been a problem. I've been cache blocking since caches were invented. And this is true. That's vertical locality management. This is a packaging issue. I do have to do loop blocking to move stuff. Vertical locality is moving stuff from my main memory into the CPU, back out again through a cache hierarchy. The thing that is different as we move forward is that topological locality, even within a single chip, so these little squares here are meant to be, this is a 2D planar surface of a silicon chip, and these little squares here are your cores on that chip. And now suddenly I need to know something about, or maybe my runtime system. Hopefully my runtime system needs to know something about how to map processes onto this to maximize the topological locality of data movement. And that horizontal data locality management is the thing that our current programming environments stink at. And, and this is something that we need to address. But that's not all that's wrong. So we're almost done with all the stuff that's going wrong, and we're going to get to the programming environment part. The memory technology has also evolved to the point, I talked about pin density, and I can go to silicon carrier technology in order to continue to crank up bandwidth for memory technology, but there's limited surface area on these silicon carriers that they have for that, so I can't get the capacity anymore because I can't fit enough of those little memory cubes in a little ring around the processor chip. And so in the past, we'd always been used to, for your main memory, I'd get target, I wouldn't always get it, but I'd target 1 byte per flop of memory bandwidth, and also with the very same memory technology, 1 byte per flop of memory capacity. And we kind of gotten used to that over the time. The new paradigm, though, is I can get you 1 byte per flop of capacity, but I'm going to be off by a factor of 100 in terms of the bandwidth that I could deliver with that technology. But I could go to stacked memory and in-package memory. I get 1 byte per flop of bandwidth, but I'm off by a factor of 100 in terms of the capacity that I can offer you. No one technology gives me both anymore. And in fact, this is from Samsung documentation. They said, this is what the future looks like, 2 tiers of memory. Nobody likes this. I can't imagine who would like it. But we asked the vendors, we said, we want 1 byte per flop of capacity, 1 byte per flop of bandwidth. They said, that's great, here it is. And they're like, well, we were really hoping with one technology, but they just split it and called it a day. And so we're going to see if we can try to migrate stuff between these 2 tiers of memory, but this is kind of an unsatisfying solution. And in general, what we're seeing is increasing depth of the memory hierarchy. Not only are we seeing the inclusion of HBM, HMC type memories, but we're also seeing additional tiers of memory in the storage hierarchy. So this is the future, and it's going to impact our programming environments. So quickly, I'm going to go through, with all of that in mind, what are we seeing as the straw man architecture that we're going to be targeting? So the first is that when we did procurement, the Cori procurement in 2012, well, we saw kind of 4 different kinds of nodes bid for this. We had heterogeneous many-core, homogeneous many-core, traditional type nodes, heterogeneous accelerated, and attached accelerator type architectures like they have on Titan. First thing that we noticed was that they offered us a choice of integrated accelerator where they had something like the NumaLink technology that they offered for Coral, where the bus, instead of PCI bus, you have a bus that's so fast that you almost don't see it anymore. The GPU can actually see the CPU memory at almost the same bandwidth that the CPU sees the memory. That's fantastic. Not only that, they have unified memory architecture with the GPUs, so it's no longer an error if I didn't CUDA copy the stuff into my fast memory. Well, if that's the case, I don't want this thing anymore. I want the NumaLink thing. So there's still a bus there, but from a logical perspective, it really looks like I've got an integrated accelerators integrated together with my big cores. I like that better. I'm never going to buy something that doesn't have unified memory again. So the next thing is accelerators versus lightweight cores. People had said, oh, the ISA is different, security is different, I got to use CUDA with one and OpenMP with the other, SIMD widths, thread divergence, cache coherence. But if you actually look at the natural evolution of GPUs, even for your cell phone, they are no longer for graphics anymore. It used to be that it was crazy, wild-eyed people like us that were trying to use GPUs for compute, but now it's actually mainstream. A lot of the regular computing functions, even in your cell phone, are actually invoking the GPU core. And this is general purpose compute, not just graphics. And this has pushed the GPU manufacturers to actually generalize the architecture to tolerate more thread divergence, to have coherence, albeit it's release consistency model, but they have a coherence model. In the ISAs, they're getting better with the compilers virtualizing that. I claim that over time, actually, the differences between these things really is heavyweight versus lightweight cores. And so now we really only have 2 swim lanes moving forward. And the question is, do I try to do it all with one type of core like we're doing with KNL? We're hoping Intel changes its mind on that and goes with something that's more the fat and thin cores. And in fact, if you just look at Cori, you look at the GPU thing that they're doing with Coral architecture, this is kind of what things are evolving towards. I've got heavyweight cores, more or less operating system accelerators, maybe run my MPI protocol stack, but then I have those lightweight cores, and these are my real compute engines. I have in-package memory, which is low capacity, high bandwidth, and I have my off-package memory where I get my capacity, but I can't deliver the bandwidth, and maybe NVRAM in that. Key is that with the heavyweight cores, data locality actually isn't as much of an issue. There might be some NUMA effects of the subsystem, but for all practical purposes, you can logically think of them as a pool of cores. It's the lightweight cores, the ones that you have to worry about, where you need to worry about what is nearby and what isn't. Furthermore, they actually can scale cache coherence across a chip that has thousands of cores in it. That it can be scaled, but the architects do also warn you, if you take too much advantage of it, you will suffer, because cache coherence has this way of obfuscating data locality. You have to probe everybody's caches to see who's got that cache line. So if you use it, you can use it, but it'll be bad. And if there's any way that you can avoid relying on the cache coherence, it'll give you a performance boost. And then the other thing is that I got integrated NICs. So NICs are moving on board the chip. Once the NIC is TLB coherent and cache coherent with the CPUs, it becomes a peer. Now suddenly I don't have to do page pinning. Now suddenly global address space looks like a really attractive thing to do. So we just made it to implications for future programming models. So this might actually work. I can't believe it. So implications. If you put all this together, you know, when I wrote, I was involved, I was one of the original developers of this code called Cactus, which was a GR code that I worked on for many years. And, you know, I think about how we designed it. We used to have these arguments over, well, what's really going to happen with the future of architecture? I mean, you can't really design a code with all possible combinations of what could happen with architecture in mind. You actually have to make choices, say, this is what's important, and I'm not going to make it infinitely scalable. I'm going to make it scalable enough. And so some of the design choices I had when designing the code, and also what people who design programming environments had in mind, was that peak clock frequency was the original limiter for performance improvement, but now its power is the limiter. Flops. So we used to think in terms of algorithm development, the flop was the biggest cost for a system, and I need to optimize my order, complexity, everything's about reducing the number of flops. But now actually the flop isn't the thing. It's data movement dominates. I need to optimize to minimize data movement. So complete reversal. Concurrency. I was expecting when I was designing Cactus that we'd see a 10x increase in concurrency every decade. And so we didn't design for infinite scalability. We designed for what was anticipated to be a slow pace. I know that the MPI developers had the same idea in mind, but concurrency is going from linear growth to exponential growth. And we didn't plan for that when we were designing this stuff. Memory scaling, maintain byte per flop capacity and bandwidth. Now we're moving to compute growing twice as fast as either capacity or bandwidth, the memory technology. Data locality, MPI plus X model assumes within a node, every CPU is equidistant to memory, and every CPU is equidistant to each other. Likewise, the MPI model, when I send a message to rank 2, I think it's, you know, logically the same distance as to rank 1,000, you know, in the system. This is no longer the case. Topology is important. We are tapering bandwidth at every level, and so you now need to have a way of reasoning about locality. Maybe not the programmer again. Maybe we need to have the runtime system involved. We used to assume uniformity of core types. We used to assume uniformity of performance. But architecture is diverged. We have fat and thin codes. We have aggressive clock speed throttling. We can no longer assume homogeneity. We have to assume heterogeneity. And then, of course, reliability, hardware's problem versus software problem. So we created this document, this abstract machine models, document to attempt to communicate. Well, the first thing is that with this, it really inverts everything that we thought was important is not important. Everything that's important for the future was not on the radar screen when we designed our programming environment. So it's opposite land. Everything is the opposite of what we designed it for. We need to address that. So, and I think that the path to addressing it is coming up with re-examining abstract machine models. So I'm going to skip from this thing and just talk really about what is an abstract machine model. There's a really good document from Martha Kim. This is a really old concept. AMMs date back 40 years, maybe 50 years. And the original parallel abstract machine model was called the PRAM model. And it is the underlying model that we had for the early SMPs that I worked on. So when the first, Cray XMPs were coming out, and then SGI Power Challenges later when I was at NCSA, the model, and this is the model that gave birth to OpenMP, was that all those processor cores are equidistant to the memory. So I can have all the details about it's a YMP, it's a SGI Power Challenge, it's an HP SMP, but underlying that is a common abstract model of how things are connected together logically. And we developed the original OpenMP model was developed with this equidistant model in mind, where all the processes are equidistant. Then we got to the SGI Origin 2000, where they continued to attempt to scale up the parallelism of the system, but they could no longer maintain this illusion that the processors were equidistant to each other at every scale and were equidistant to the memory. And if you programmed with this abstraction in mind and ran on an SGI, you would suffer greatly for that. And so, at that point, we just determined that, it's better to just program for locality as a default, and at the end of the day, the SGI ended up being a very good MPI machine for us. And once we cracked, decided to go and with the CSP model, the Communicating Sequential Processes model, then also MPI became palatable. CSP basically says I have a processor and memory is local, and then for non-local memories and processes I have to send messages between them. And it sounded like a crazy idea at the time, but once you get over the hump and redesign your algorithms for it, it's great. So CSP is the abstract machine model. MPI is the concrete embodiment of a solution, a programming environment solution to that model. So we've had that model. There's another model which is what we call MPI plus X. There's actually an abstract machine model for that. It's called candidate type architecture. Terrible name for an architecture, but the question is that what's next? Is MPI plus X sufficient? And I claim it isn't. And all of the stuff that I described before, I think that the candidate type architecture is the incorrect abstract machine model for programming these machines. And why do I think that MPI plus X is insufficient? Well, first thing is the lightweight cores aren't fast enough to process the complex protocol stacks at speed. When you're doing tag matching, when you're doing stuff like that, the thread match and dispatch operations are very inefficient. Even the interrupt management is inefficient. It is much better, and the architects have even told us that it's much better to use something lighter weight, like using the memory address to match endpoints, because that capability is already baked into the hardware. We can't ignore locality anymore, especially inside of the node. We have the NUMA issues aren't just between chips anymore, it's even within a chip. We have new memory classes and memory management. MPI plus X doesn't really address this, and there's asynchrony and heterogeneity. And again, bulk-synchronous model does not address this challenge. So, what's wrong with MPI 3 plus OpenMP? Well, I know that it'll work. It's already working now. The issue that I have is it doesn't offer much of an abstraction. I have to create my own layered abstractions on top of it. And in that sense, I think it'll work, but I also think we can do a lot better. And here's why. So if you look at the old model, parallel do, I got a loop. I slap on an OpenMP parallel do, now it's parallel. That's great if my model was the PRAM model. But my model isn't the PRAM model anymore. So the old model was I equally divide compute work and spread it out amongst the processor cores, and data just magically moves to the right place. But if data movement is the dominant cost, then this is the incorrect abstraction for parceling out parallel work. I need to have a way of minimizing data movement. So I want to describe logically how the data is partitioned across the machine, and then have the compute follow where the data is located. So this is a data-centric model. This model actually, by the way, is, MapReduce and Hadoop do this model, but MapReduce and Hadoop are wholly inappropriate for loop-oriented codes. But the notion is this is a statement from UPC where I've already partitioned the array A, and when I do a parallel do loop, the loop iterations execute where A is local. And so this is a data-centric programming model, and that's inverted from the way that OpenMP was fundamentally designed to work. But that's all right. Standards evolve, so they have OpenACC, which was inspired by OpenMP, and it includes things to manage data locality. Well, this is from John Levesque, who is a great programmer, and this is what it looks like. These are the embedded comments for OpenACC for the code that's below it. I'm not so crazy about that, and John Levesque is a conserved quantity. I can't replicate him very easily, so I'm not sure it'll work. And this code, by the way, works phenomenally well, but I'm not sure if I want to do that. OpenMP4 isn't much better. This is in the OpenMP4 documentation. I have 3 times as many lines of code in comments than I do actual lines of code. For a very, very simple loop, I have a lot of stuff. And I also have to change all that stuff if I work on a GPU. The stuff in this comments will be a different set of directives. So it's portable, but not really that portable. It doesn't look much better in C. It'll work, but do I want to do that? No. Let's also look at messaging overhead. So this is the cost of doing nothing with iSend and iReceive on a Cray. So it's very highly optimized implementation of MPI. I do an iSend and I don't even post a wait. So it hasn't actually transferred any data yet. And this is how many cycles it takes off node and even on node. I'm spending 1,000 cycles just to do nothing. And this is because I have to navigate the MPI protocol stack. Well, that's on a Haswell core, and that's taking, 1.6 microseconds in order just to navigate the stack. Now imagine I have a KNL core. How many cycles is it going to take for a core that's lightweight to do that? Well, it takes 3 times as many cycles for each core to navigate that stack. And hell, what if I had a GPU core, had to actually send an MPI message, do tag matching, and execute that stack? I only actually get an execution slot once every 8 cycles. So now we're like 3,000 nanoseconds. So what is 30,000 nanoseconds? So that's 30 milliseconds spent just to send nothing. If I need to strong scale, that is a problem. I'll skip this one here. We're starting to run out of time here. So you think you can do better? Well, I know MPI and OpenMP will work, but OpenMP and MPI need to evolve. So whatever OpenMP and MPI is, when we get to Exascale, it isn't going to be the same OpenMPI and OpenMP and MPI. We all have to change. I think it's a lie perpetrated in our community that just because we're going to continue OpenMP and MPI, that somehow that means we don't have to change. Even if you use OpenMP and MPI, it's going to be different. Otherwise, your code's going to stink. So, let's look at the alternatives. So we got data locality, parallelism, overhead, performance portability. There are abstractions, such as, for example, data locality and parallelism. Tiling abstractions are an excellent way to overcome those data locality problems, and we have examples with TIDA, hierarchical tiled arrays, Raja, Cocos, that people are actually implementing these abstractions as usable APIs that programmers could use. For communication overhead, we've always had PGAS. It's just not been ideal. With the changes in computer architecture, though, the hardware architects are saying, please just allow us to use addresses for sending messages rather than tag matching and type matching and all the other matching. Now my hardware can give you 0 overhead data transfers if you would just use memory addresses. So why don't we use memory addresses? These are things that have been around for ages. UPC, UPC++, MPI3 RMA, CoArray Fortran, which is now Fortran 2008, and OpenSHMEM. They're already there. Performance portability, DSLs, auto-tuning, heterogeneity. There's a lot of people studying data flow is back in vogue again. There's a number of different runtimes, Legion, Charm++. By the way, Charm++ predates MPI. HPX. There are a lot of alternatives available, and then there's, of course, containment domains and RX solvers for resilience. And so I'm going to just take the last 10 minutes or so to close this out, and then I'll take some questions here. So I'm going to just give you a few vignettes of what these things look like that I was just telling you about. I think I already gave you the introduction to a data-centric computing model. We actually examined a number of different people that are doing this. We even had a workshop about this that I'll plug in just a second. But the common theme that we've seen people adopt is programmers would like to, when they move their code to new architectures, they just want to minimize the number of lines of code that they need to change in order to migrate to a new machine. So how do you make that work with a data-centric programming model? Because right now, when it comes to managing data locality, I have to change my loop blocking. So I end up changing the loop blocking for every single loop in my code. And so I have to touch a lot of code in order to manage structure of arrays or array of structures or any of the data locality optimization tricks. So the idea here is that instead I describe my data layout, my domain decomposition. It becomes an intrinsic part of the data type. So when I declare a multi-dimensional array, I also include additional metadata that describes how that array should be laid out. Now, when I move to a new machine, I have to change that description, but I only have to change it in one place. And then when I hit my loops, I use either C++11 lambda functions in order to abstract the iteration space and separate it from the data layout. Or, in TIDA, we have our own construct, which is essentially a lambda function. In doing this, I can change my code in one place to describe abstractly what the logical domain decomposition is. And then when I hit each of my loops, then the lambda function allows me to actually visit the data in the correct order. And then the runtime system makes the logical to physical mapping so that I don't have to manually do the thread pinning, which is what I have to do now with Freak and OpenMP, is do manual thread pinning. So this is a data-centric programming model, is actually representing information that the compiler would otherwise destroy about data locality and actually preserve it as metadata, which can be understood by the runtime system and also understood by runtime constructs when you visit your loops. I'm going to skip this. This is abstraction. This is what it looks like. The key is that after I make these transformations to my code, moving to new architectures, I go from naive OpenMP performance to having naively written code that performs as well as code that was hand-tuned by one of our experts. This is what you get if you change and adopt an abstraction, a durable abstraction that's parameterizable. It enables you to write naive code again and expect to get performance that you'd get from manually loop blocking and generating ridiculous amounts of code. simulations as we scale out to thousands of cores. So we had a workshop in this, and what we determined was that there's many people who have adopted the same thing. We all are actually using essentially the same recipe. Raja, Cocos, what they're doing in the European Union for these things. We actually think this might be a huge opportunity for standardization programming environments. And so we had our first workshop at Lugano. We had a second one in 2015 in Berkeley. We're trying to finish that report, but you can see the initial report in the 2014 workshop, and it scopes out the design space of what's happening in this space. And so I think it's really promising. The other is domain-specific languages. This is, I raise the level of abstraction so that right now when you write Fortran code or C code, it overspecifies the solution. When I have a for loop, it has to assume, the compiler has to assume I have to execute in exactly the order that for loop implies, 1 through n, in order to be correct. And I have to use Herculean proofs or polyhedral methods in order to prove that I could do anything otherwise. Way over constrained. If I want to have flexible parallelism, I raise the level of abstraction. I can do it by using a higher level meta language. And that DSL then can write, let's see if it comes out on the screen. So you have a very simplified high-level description of what your intent was, a PDE solver, block structure grid, and it generates the optimal code for different programming targets. And this is in fact used in practice right now for a lot of image processing applications. The question is, can I apply it to scientific codes? And certainly the tensor contraction engine is a good example of this, but there seems to be opportunities in particle codes and PDE solver codes for applying these kind of DSLs. So I can target, use the same piece of reference code and create target GPU and create optimal code, target a CPU and create optimal code. So low overhead messaging, I told you about this already, where the challenge is we have been depending on weak scaling to hide the overheads of sending messages, which haven't really improved each generation. But great thing is that weak scaling has enabled us to move forward. But when I need strong scaling, I have to, and this is where I don't increase my memory size each generation, then that means I need to take up the slack by doing twice as many iterations per time step. So I need to have a performance improvement in order to take up the fact that I have to take steps that are a quarter the size. So that means if I have no clock frequency increase and I'm getting everything from doubling the number of cores, I really need to focus on strong scaling. And this is hard. This means I have to reduce overheads. And the only place that I can think to reduce overheads in these machines is actually by improving, reducing the overhead of sending messages. In 3,000 cycles to send nothing, that's just ridiculous. The architects are telling us this. The architects are saying, I have now had to bite the bullet, and I have to use a packet-switched network just to move cache lines to the correct location on a chip that has hundreds of cores. And the packet header, the address, is the memory address. So I already have the hardware to do zero overhead messaging. It's already on the chip. What it takes for me to make that your main messaging layer for moving messages everywhere in the machine is, with no overhead, is minuscule in terms of hardware design. So why do we look a gift horse in the mouth? Why don't we just do that? So, this is MPI3 RMA, has puts and gets. It's even better if you go with PGAS language. I have memcopy. Suddenly memcopy works as well within the node as it works between nodes. It becomes the same. I don't have to have MPI plus X. I can have X. So I'm going to end this. I have a lot of vignettes on different programming environments issues. The rise of data flow, it's back, functional programming and data flow. The point is that we have been doing SPMD. It's become a dominant approach to parallelism, but it used to be vectors were our execution model for parallelism. We also have successful things with dynamic threads with fork join and event-driven execution in the business. area, why don't we due diligence examine other execution models? Just because we've been doing bulk synchronous doesn't mean we have to continue to do it, and it's incumbent on us to examine the alternatives. So, all right, post-Morse, Toshi already told you about this, and we're just going to get to the end, which is the emerging hardware constraints are increasingly mismatched with the current programming paradigm. Current emphasis preserves flops. The real costs are not flops, it's data movement. It requires a shift towards data locality-centric programming paradigms. And I think that OpenMP and MPI, we will evolve them into the future, but they weren't really designed with this in mind. So it'll work, but I think that there are alternatives that exist that don't look as clunky, and we should study those alternatives. You know, the biggest opportunities for energy efficiency and performance improvement are where you really examine what is the easy path in the hardware and work together with the hardware architects to come up with a compromise solution that minimizes disruption to the software environment, but leverages things that are natural design trends that are going out for the next 20 years. And in that way, you can develop durable abstractions that will last. So you don't have to rewrite your code for another 15 years or so, and then the end of Moore's Law, and then you're screwed. So, all right, that's it. Thanks.